Hi, welcome to Physical Science. This is 3.3a on energy. Today we're talking about the charts, graphs, equations, and then next time we'll be talking about calculations. So what is energy? Well, the definition of energy, and you do need to write these notes down, is the capacity for doing work or producing heat. The conservation of energy is that energy cannot be created or destroyed. It's actually a law of conservation of energy. It can only be transformed from one form to another. It can also be transferred from one form to another. And today we're going to look at both types of mechanical energy, potential, which is Eg, and kinetic, which is Ek. So let's start with potential. You have a pendulum example. A pendulum is just a bob. The thing on the bottom is known as a bob, and it's hanging on a string supported by the ceiling or anything else above it. Energy is associated with height for potential energy, and it's height above its normal low position. So when the pendulum is raised from position D to C, it gains potential energy. When it is raised all the way to position A, its highest point, all the energy it has is potential. Kinetic energy is associated with an object's motion, and it depends on mass and velocity. When the pendulum moves from position A to B to C, it gains kinetic energy. At position D, it will be all kinetic energy. So we have a transfer of energy from potential to kinetic in this example. We are going to learn to chart that energy, and pie charts are a really good way to start viewing the amounts of energy possible. If position A has all Eg because it's at its highest position and position D is all Ek, those pie charts may look like a simple circle labeled all Eg and then a same circle of the same size labeled all Ek. Notice the color change is a good idea to differentiate your Eg and your Ek. But what about in between? How would we graph those? Well, as the pendulum swings to its lowest point and it's moving its fastest, all the energy is transferred or converted from Eg to Ek. But partway down, it's gaining kinetic energy and losing potential energy. So we might draw those graphs as mostly Eg and partially Ek, and then mostly Ek and partially Eg. Notice that the pie chart itself doesn't change size, we just apportion the types of energy differently. From charts to graphs, although pie charts are good, most of the time we're going to want to use a bar graph. And a bar graph has 4 blocks of energy that will represent all the energy, as if you could divide your pie into fourths. So at position A, we would have all Eg, so that would be 4 blocks of Eg. At position B, because I can't have part of a block, I might have 3 Eg and 1 Ek. Position C, I might have 1 Eg and 3 Ek. Because neither one, position B or C, is halfway down, I don't want to split it as 2 and 2. And then position D would be all Ek again. Notice in the bar graph, I have labeled Eg and Ek because those are the types of energy that are available at each position. It's not necessarily used at each position, A, B, C, and D. So now from charts to graphs to equation, you're going to be given an example of a ball bouncing. What is the pie chart, what is the bar graph, and what is the equation that would go with it? Well, if this is your example, notice that the arrows above indicate that it's moving. So this ball has been bounced. It is coming directly up off the floor, so it has no height. But at position B, it does have height. C is the highest it will go. D is halfway down, and E is right before it hits the ground again. And again, notice the arrows are showing you the direction of the motion and how much motion it has. The longer the arrow, the faster it's going. So the pie charts for this might look like this, A being all EK, B being half EG and half EK, C being all EG, D being half and half, and E being all EK again. The bar graphs would then be similar. Position A has all EK, position B has half and half for 2 and 2, position C has all EG, position D is half and half, and position E is all EK. Now the equation is just the bar graph as if you had to read it out loud. So it looks like this, and it's read the EK at A is equal to, and that equal sign is incredibly powerful because it tells you that all the energy that you have at A, you have all that same energy at B. So this is the EK at B plus the EG at B is equal to the EG at C is equal to the EK at D plus the EG at D is equal to the EK at E. This is the kind of problem you're going to be doing in class today. But there are two additional forms of mechanical energy that you need to be aware of. They are ETH. It is actually known as thermal mechanical, and it comes from friction. It's what causes objects to slow down. And then you have EEL. EEL is mechanical elastic energy, and it comes from springs or bounces, if we're going to look that deep, within an object. So you also need to be looking for those two types of energy as well. Thanks for watching.